Now we're going to learn about motion diagrams, and we're going to do our first example problem, which is problem 24 from Model 1. So before we begin this, I would like to give you some advice for this course. So when you're watching the lecture videos for a particular section and you feel like you kind of get the hang of what we're doing, I would encourage you to pause the video and try to finish the problem on your own or go as far as you can go without getting stuck, and then go back and look at the video and check your work. Um, I might go fast through the math. So when we get to the problems where we're doing solving equations, I would encourage you to pause, work through the math on your own, and then go back to check and make sure that what you did lines up with what I did. And you also might find that for a particular problem, I'm going a little bit slower through the math. So also you could pause the video there, do the math on your own, and then you can skip over where I'm solving the equation as long as you get the same result in the end. Okay, so take advantage of the fact that these are recorded lectures and use that pause button if you need to. Try and do the problems on your own when you feel like you're getting the hang of it. Pause it if you need more time to go through the math. And if you feel like I'm going through the math too slowly, then feel free to skip ahead. Okay, so today we're going to learn about what a motion diagram is. So here on page 9 of Spiral Physics, we have a motion diagram for a car. And in our first motion diagram, we have actual pictures of the car, and then since we're going to treat everything as a point particle, we're just going to make the car into a point particle. Okay, so you can picture of this as a multiple exposure photograph, and we're taking a picture at equal time intervals. So you can make the time interval whatever you want, but let's just say every 1 second we take a picture, and all these pictures are going to show up on the same photograph. Now, in order to interpret the motion diagram, you have to know what direction the object is going in. So it would be helpful if we said, well, this is the first picture of the car, and then this is the second, the third, the fourth, the fifth, and this is the sixth. If it was the other way around, and this was the first, and this was the sixth, then the car would be going in the opposite direction. So that's something that we need to know in order to interpret what is happening in the picture. Okay, now if this was the first picture and this was the last picture, think about this for a minute, pause the video if you have to, and answer the question, is the car speeding up or slowing down if this is the first picture and this is the last one? Okay, so if we start here and we end here, because there's less distance between picture 5 and picture 6, if these pictures are taken every 1 second, this means that the car covered less distance in the same amount of time, so the car would be slowing down. So if the car is going this way, the car would be slowing down. And if the car was stopped, then all the photographs that you took, the car would be at the same place. Now, if the car's going the other way, if it started here and it ended here, so if it's moving from right to left, then there's more distance between each successive image, and then the car would be speeding up. And think about for a minute what would happen if the car was moving at the same speed. So if the car was moving at the same speed, it would cover the same amount of distance in equal time intervals, so all the images would be the same distance apart. Okay, so that is how we're going to show position on our motion diagram. And this is enough for us to get started on part A of problem 24. Okay, so you can turn there in your textbook. And for problem 24, we have a subway train in Washington, D.C. It starts from rest and accelerates at 2 meters per second squared for 12 seconds. Now, the first thing that you need to be aware of here is that you're given more information than you need in order to be able to successfully draw the motion diagram. The reason for this is that some of the problems that you see in the beginning of this section, when you're just drawing motion diagrams, they're actually going to appear later on. So you can think of this as if you were drawing the motion diagram as the first step step in being able to solve the problem, but you're actually not going to solve the whole problem now. You're just going to draw the motion diagram, which means that the 2 meters per second squared and the 12 seconds really don't matter. All I need to know is that the subway train is starting from rest, and if it's starting from rest and accelerates, it must be speeding up and not slowing down because it started from rest. Okay, so I'm going to start on the left side, but you can start on the right side, and I'm going to show you in just a moment how you will indicate what direction the subway train is going in. Okay, so if I start on the left side, if it's starting from rest and accelerating, that means speeding up. That means the space between my dots should be getting larger and larger. And then, okay, so for right now, all you need to show is that the space between the dots is getting larger and larger. And because we're in model 1 and we have constant acceleration, the space between the dots should be getting larger by the same amount. So we're going to talk about that when we get to acceleration. Okay, so this is position for the motion diagram. Okay, so now I'm going to move on to page 10, where we are determining velocity from a motion diagram. Now, for position, we're going to use meters for position, and for velocity, the units will be meters per second. If on your motion diagram here, you want to measure the position of the subway train, first of all, you would have to know the scale. We can make the scale whatever we want here if we're ignoring the 2 meters per second squared and the 12 seconds. So let's say this is 1 meter. And we also have to know what the time interval is, and remember that for each one of your dots, it should be taken after the same time interval. So this would be 0 seconds, and if our time interval is 1 second, this would be after 1 second, this would be 2 seconds, 3 seconds, 4 seconds. So if I want to find the velocity, I would do the change in position over the change in time. So for position, we're going to use an R. So delta R over delta t, that would be the change in position over the change in time. And if delta t is 1 second, that would be 1 meter per second for our first time interval here. Velocity is a vector quantity, which means it has magnitude and direction. We don't have to be terribly concerned about that in Model 1 because we only have 2 choices for direction. The object can be moving forward, or it can be moving backward if we're looking at horizontal motion, or for part C and for part D, we're going to look at vertical motion, and the particle could be moving up, or it could be moving down. Okay, so we're going to show the velocity using a vector which has length for magnitude and is pointing in a direction. And all we have to do to indicate velocity here is to connect the dots. So if I connect these 2 dots and draw an arrow in the direction that the object is going in, this is my first velocity vector. And this is what I would get if I did this change in position over my delta t time interval, which let's pretend it's 1 second. Then if I go from position 2 to position 3 and connect the dots, I get my velocity vector for the second time interval. If this is 1 meter, then this would be 3 meters. So as I go from here to here, the average velocity is 3 meters per second.